Good morning. We want to welcome you to this morning's webinar put on by Voxelmaps. Just a couple of quick things. My name is Brian Soliday. I'm Chief Revenue Officer at Voxelmaps, and I want to welcome you and appreciate your participation in this webinar series. If you have any questions for us, please provide those questions via the Q&A buttons on the bottom of the screen, so you can get access to that. And we're recording this session, and we're providing this to everyone after the event. We ask, please feel free to pass this along to your colleagues that could not make it today. We'll also be providing you access to a guidebook, which has links to all the webinars we've done, and then a special section really on one of the topics we're going to talk about in a little bit, that being the U.S. infrastructure bill. And so we'll have a lot of good information about the geospatial opportunities within the infrastructure bill that we'll be sharing with you. Well, today, the agenda is going to be pretty broad, and then it'll be broad at first, and then really dig down and focus on the utility and telecommunications sector. So Peter Atalla is going to give us a brief overview of Voxelmaps as an organization, and then talk about the concept of maps for machines. And that's really important to what we're going to be showing you today, is that, that map for machine technology and the philosophy. Peter will then talk a little bit about our technology and volumetric mapping 101 and what it really means, the data collection systems that we put together and we've deployed in the field and we're using today on a global basis. He's then going to talk a little bit about the 100 cities DAS data set and the activities we're doing around that in terms of building this digital twin archive of the planet. I will talk a little bit about industry use cases, and then I'll close out a bit with talking about the U.S. infrastructure bill and providing you with some really solid background information on that. And then we'll close it with questions. And as I mentioned, just go ahead and submit your questions via that Q&A pod at the bottom of your screen. So with that, I'd like to introduce to you Peter Atalla. Peter is the CEO and founder of Voxelmaps. Peter, go ahead.
Thank you very much, Brian. Hello, everybody. It's great to be here today and have the opportunity to tell you a little bit about what we're doing at Voxelmaps and how it can also relate to some of the challenges and projects that you guys have on as well. So I just want to start by setting the scene a little bit, just giving the company background. So Voxel has been going for about 4.5 years. We were actually a spin out from an existing mapping and navigation company called NavMe, which was based out of Europe. And so NavMe was quite well established. It was had about 30 million users of its navigation applications around the world. But more importantly, it mapped 180 countries around the world. And so it was a big project, 10 years, collecting about 7 billion kilometers of data, and involved tens of thousands of people doing that. But about 5 years ago, there was a division within NavMe that was really looking at the future of mapping and what that should be like. And that really became Voxelmaps. So we were separated and spun out. Voxel's head office is now in San Francisco, and we're an entirely independent company. We've grown quite a bit since then. So we have 6 office locations around the world. So San Francisco is the head office. We have a number of other centers across the US. We also have Mexico City. We have the UK. We have Portugal. We also have Singapore and Australia. So we're about 350 people and growing pretty quickly at the moment. But as Brian mentioned, I want to really start off by kind of explaining a central sort of theme in terms of the technology we have. And this is really around the concept of building maps for machines. So I want to start off by explaining the difference between a human map and a machine map. So human maps, we're all very familiar with. These are the maps that are in our cars, on our phones, on the web, for example. And really they're around 2 use cases. One use case around navigation, so navigating people to an address, which could be a city or a building or a street. The other use case is really around visualization of geodata, so kind of creating these geodata layers on top of the map. The majority of human maps are still 2D. There are some 3D elements to it, but it's not extensive. And it's pretty low resolution. So we're talking 1 to 3 meters in terms of accuracy. Now, if we compare that to a machine map, it's very different. Firstly, a machine map is a true 3D model. So really, it's much more of a model than just being a map. And by that, we're analyzing every object we see in a given environment. So in cities, that can be not just the buildings and the roads, but infrastructure, telecoms, utilities. And in non-urban environments, it can be things like vegetation, land structure, land classification. And we're doing this at very high resolution, so 1 to 4 centimeters in terms of resolution. So at that kind of resolution, it's not just about locating where an object is or a building is, for example. It's also about getting information about those objects as well. So accurate measurements, attributes, features are very, very important to us. So when we talk about machines, it's everything from computer models and artificial intelligence models to better understand cities and 5G signals and the environment, all the way through to modern forms of autonomy, whether that's autonomous cars or delivery robots or AMRs, which are automated miniature robots, or drones, for example. And there's a requirement for this data not just to be outdoor data, but also indoor data, even subterranean and ocean data. So it's one complete model. And so that's what we're really building. And the way that we do this is to use quite a unique approach of volumetric mapping in comparison to kind of standard 3D mapping. So I want to just explain the difference between the two. So here we have an example of a 3D map. This is from Google, but Apple has similar maps, so does here. And these are great maps for humans. Again, this is a visualization technology. So we have a map, it looks very pretty, you know, it describes the city pretty well. But when we zoom in, and it is 3D, but when we zoom in, we see that the map is pretty low resolution. So essentially all of these 3D objects are just very basic meshes with a texture placed over them. Again, for visualization, it's totally fine. But if we were to perform measurements on this, it wouldn't be very accurate. And furthermore, inside all of these meshes of the buildings, there's no interior information. You know, it's just an empty hollow mesh. And that's because when we're looking at using mesh technologies, meshes are just focused on one aspect of physical matter, just the surface information, not so much the interior information. So again, for a visualization tool for humans, this is absolutely fine. But a volumetric map is very different. So a volumetric map involves creating a model that not only models the surface information of matter, but also the interior information as well. So to do this, we use voxels, which I'll just come on to and explain, but it essentially allows us to map everything and do it in a way that we can collect different types of data, for example, indoor data, and that data will instantly just drop into the model without any human involvement. So the ability to have real-time updates is actually very important. And again, we do this at very high resolution, as I mentioned, 1 to 4 centimeters, and we add a fourth dimension of time to be able to do things like change detection. And I'll show you some examples of that as we go through. So the technology that we use is using voxels. And I'm sure some of you have probably heard of voxels by now. But a voxel is just a 3D pixel. It's a volumetric pixel. And voxels by themselves aren't new. They've been used in computer games for quite a while. So Minecraft, for example, is an example of a voxel rendered world. But they've also been used in areas of robotics. And actually our technology is kind of quite close to the robotic approach. It's using voxels in a configuration called a VOG, or a voxel occupancy grid. And so the use case in robotics is you normally have a small robot with some kind of 3D sensor on top, and it would go into a room and it would make a very basic three-dimensional voxel occupancy grid, a voxel matrix, if you like, of the room so it could navigate its way around. So we took this idea, but we applied it to the planet. So the actual technology here is called a multi-resolutional voxel occupancy grid. So we took the Earth and we placed a giant mega voxel over the top, a giant cube. And inside this voxel, it's full of multi-resolutional voxels. So theoretically, they can be absolutely any size. For our purposes, we use 8-meter voxels down to 1 centimeter voxels. Now, each voxel has a unique position in space and a unique address, a permanent position space and a unique address. And this model is what we call an Earth-centered Earth fix. So it means it starts from the interior of the planet and works outwards, from the center of the planet outwards. So it's through everything. It's not just surface information, it goes straight through the Earth, through the ocean, through all of the buildings. Wherever you're sat at the moment actually is full of these virtual voxels. But to start with, they're just empty. It's just a 3D georeferencing system. So what we have to do is validate what we call the occupancy status of the voxel. Basically, is it free space or is there something in it? So the primary way of doing this is using LiDAR. So if the laser beam from the LiDAR passes through a voxel and it's not reflected off anything, then we label this as free space. But the moment it's reflected off a surface, we collapse down to the smallest unit of the voxel, currently 1 centimeter, and we label this as occupied. So in effect, what we're doing is etching out the matter of the planet. Now, by doing this, really what we're creating is this global spatial database for 3D and 4D data. It basically is a superior technology to build a digital twin from. And some of the great things that it enables is real-time updates of the data. So you don't need to do human pre-processing of meshes to try and get 2 different kind of relative meshes to merge together. All of this happens instantly. And it's persistent at a global scale. So it's actually designed to handle planetary data, thousands and thousands of petabytes, and keep that live. So we don't view 3D data just as data you put into a viewer or a CAD application. It has much bigger reach than that. And so some of the really cool features that you get with voxels in comparison to using things like points or meshes. So firstly, a voxel is a measurement unit, a 3D measurement unit. So it's very easy to perform calculations within voxel space. Secondly, on the surface of the voxels, we can layer on additional information. So for example, camera data. So we take the RGB values from the camera and put it on the surface of the voxels to give an aspect of color. But it can also be hyperspectral imagery. It can even be radar as well. So with the voxels, we have the shape. With the surface data, we have this element of color. And it's at this point that we apply the artificial intelligence. So deep neural networks working in 3D to recognize what different collections of voxels are. And it can do this, and it's fully 3D. It's not just a 2D pixel-led approach. It's fully analyzing the object in 3D and voxels. But it can also analyze what's here at the moment. But then every voxel has an infinite number of time states. It has like a temporal data component. So that's interesting because it allows then the AI not just to look at what's currently here, but also to look at what's been there in the past and compare and contrast the two to do things like change detection. And we'll show you some examples in terms of use cases around that. So when you combine this then with the concept of the permanent addressing, the global spatial database, the ability to intelligently search and pull back information, it becomes a really powerful platform. So I'd like to show you what this actually looks like. So this is a digital twin that we created using Voxelmaps. This is occupancy alone. This is in San Francisco. We then layer on to the surface of the voxels the camera data, and then the artificial intelligence is recognizing all the features. These are the colors that you see here. And then it automatically vectorizes that data so that we can then play around with it. We can remove things that we're not interested in or export them into different data formats or put them all back and focus on the entire scene. Currently, the system is trained to recognize about 100 different features in cities at the moment. Very soon, we'll be up to about 200 features, and we're doing the same for indoor spaces as well. But we have the ability to also train to recognize custom features. So if there's any object or feature that humans can see and identify very well, then we can do the same thing with great degrees of accuracy. So once we've collected the data and we've stored it in this voxel format, it's this platform, which we call Voxel Insights, which really extracts out the intelligence from the data set. So these are screenshots from the system. Every time you see a colorful line here or a colorful box, this is a recognition event. It's the AI recognizing a feature and performing calculations on that feature. And it does that very, very rapidly as well. Also from this interface, you can select the features you're interested in, export them out into pretty much any other formats, so it's compatible with other software that's out there. But also you can do some quite interesting things in terms of things like virtual surveys. So the ability to explore the data. It's very much like a games engine here that you can go in and actually walk around. In fact, if you have a VR headset, you can exactly do that as well. So it's a very powerful tool to look at the data. But in addition to that, we provide this interface also on the web as well, so you can access the data on the web. And we provide additional tools to also train different forms of AI to recognize new features. So we can absolutely do this for you. Some customers just come to us and they have a request, and we train the networks, and they will go and find the features and extract them. Other customers like to have that flexibility, and so this is a video just demonstrating this. This is the annotation process for annotating an object. Here it happens to be a tree, and so we can allow customers to do this themselves. And once they've trained those networks up, the networks can then run across the entire data set that they have access to and extract all of the features and export those as well. So again, combining this with the desktop version, the virtual reality version, there's lots of ways to get in and interact with the data as well. I want to spend a few moments talking about the data collection side. So we have our own mobile mapping solution as well, which seamlessly works with the Voxel model. We also have the ability to ingest data from other mobile mapping solutions or other LiDAR solutions as well. So that's definitely a possibility. But one of the key advantages here is we wanted to create a platform that was very easy to deploy to make it very efficient. So you don't need to have more than one operator to do this. It doesn't take a lot to install it onto a vehicle. And so this platform here is called Symbo. It's a relatively small device. It takes one person about 10 minutes to do an initial install, and then 5 minutes to take it off and put it back on. The device can be taken off and stored in a Pelican case, so it's very easy and convenient for traveling around the country or even internationally as well. You can obviously store it in your hotel room, and having that flexibility of putting it on different types of vehicles. The device combines LiDAR, cameras, a full edge processing, so it's actually running NVIDIA graphics cards inside, and it doesn't need to have a computer that it's connected to power it. It has a high accuracy GPS and IMU, has the facilities to use RTK and PPK, and it's also 5G enabled as well. So if there is 5G, you have the ability to offload using 5G. If not, you can do that in more traditional ways as well. The only thing that people need to operate this is an iPad. So it's a very, very simple device to use. We also have a new version of this that's coming out and using 2 sensors. This will be available actually in September, the end of September. Pretty much very similar kind of specifications, but this is better for scanning higher buildings and higher objects as well. So that's imminent. In addition to the hardware, we also have tools which make it easy to do mapping tasks. So it really starts around the mapping missions. And so this map mission planner that we have facilitates that. It's an online system that you can select an area, whether that's a city or a state or even an entire country, and it will cut the area up into daily mapping missions, which can then be assigned to operators. So the operator will get their iPads, they would see the missions that they have to do. We'll even provide turn-by-turn navigation to optimize the collection process. So what they would actually see as they're using it is this interface. Again, very simple to use. So if everything's green on the device, it means it's all working. If it isn't, there's ways to troubleshoot. And also we can remotely connect to the device. So we can do remote support, which is very, very useful. As they're collecting, they see the trail of where they've been, so they can keep track of progress. But most importantly, it gives them some immediate feedback. So where the lines are green, everything is good. But if the lines become amber or red, then it means there's problems in the data. Maybe the GPS signal might have had some issues. The great thing here is by giving this information in real time, it allows the operators to go back and redrive or recollect immediately versus working this out a few weeks later in post-production and then having to send people back out as well. Now, we can run projects end to end. So very often we provide our vehicles, people, sensors, we do the collection, the processing, and provide the customer the data. But for some customers, they like to take control of this part as well, which is absolutely fine. So we can enable them to do that. So kind of summing up, well, looking at some of the benefits really in terms of Voxel Maps. The key one, using Voxel Maps technology, we can map faster, we can really reduce the cost. So, much quicker than doing some of the traditional mapping processes or survey processes can be replaced by single operators using the hardware and the technology. And again, it's not just about mapping, it's also about measuring everything as well. So accurately pulling back those features and information about the device. For example, if it's a pole, the size of the pole, where it's set back off the road, pole IDs, all of the additional information that would be required. It automatically extracts all of those things. And by doing it in this way, by building a voxel map, you have the ability to map absolutely everything that is visible. So even if you're only interested in a few assets, you have the flexibility in the future to be able to go back to the data and to essentially recognize and extract different assets which may be of interest. It doesn't have to be a brand new mapping project, making it much more efficient for everyone. Now, just before I hand back to Brian to talk through some of the use cases, I want to just tell everybody a little bit about a new project that we're doing at the moment called the 100 Cities model. And this is a data as a service model. So this is where we're collecting at the moment 100 of the top cities, the top metro areas across the US. The data will be available, ready to go off the shelf, kept up to date as well. The majority of the data set will be ready in Q2 next year. And so this becomes very flexible. There's no kind of lag time to wait to go and do a collection. This will include the full 3D voxel map, the LiDAR point clouds, the high resolution imagery, all of the features that are extracted and vectorized, and the ability to obviously have those in any data format as well. And we can be very flexible in terms of delivery. That can be either as a data as a service interface, via the web, or if there's a lot of data, it can be via Amazon S3, FTP, or even physical hard drives if that is required. Just some examples of what this looks like. This is San Jose, which has been mapped, again, done incredibly high resolution. This is all mobile mapping. We've just zoomed out a little bit in 3D so you can see it. So incredible detail of the whole area. But again, it's not just this 3D model. It's the fact that everything is automatically being categorized by the AI, and the features have been ready to extract. And we can see here a great example of kind of utility infrastructure. You see a lot of cabling and transmission wires and infrastructure. Again, this has all been scanned to incredible resolution. And again, all of the features automatically extracted as well. So with that, I'd like to hand back to Brian, where he can take you through some of the real world use cases. Thank you.
All right. Again, just if you do want to, if you have a question and want to submit a question, make sure to use that Q&A pod that we have available to you at the top or the bottom of your screen. So what I want to do is I want to talk a little bit about real world applications and use cases and projects that we've been involved in terms of using the technology. So there's a lot of different uses of the technology, and just a number of them are listed here in terms of applications and use cases. So it's for this group here, it's a lot of things like vegetation encroachment, vegetation management, joint use, make-ready engineering, right-of-way assessment, looking at the electrical distribution network. So a wide variety of potential use cases. So one that we found a number of our customers have asked us to do is this utility asset inventory. So using, in this case, it was actually aerial LiDAR. So we can use multiple different data sources. So we're really data agnostic in terms of the voxel structure and the manipulation and the use of the Voxel Insights platform, the VIP platform that Peter mentioned earlier. So in this case, what we did was we took that content from the customer. We did the data processing, ingesting it into the Voxel 4D volumetric data model. And then we did the automated feature extraction using the VIP AI ML based technology, and then validated those assets that we extracted with their existing geospatial database that they had stored. Another one that you're all probably familiar with is joint use audit. So really field inventory of all the pole attachments and what's attached to the pole and where and at what height and what distance between them, et cetera. And so the incorporation of the LiDAR and the imagery allows you to do that and identify where, electrical and the comms and the fiber and whatever other attachments, signage, et cetera. And we can then create that information and use it to update the records of the location as well as the ownership and assets of each pole. And it can be used to identify, potential NESC violations as well. Make-ready engineering is another use case where the technology can be used for. So, lots of talk here about fiber make-ready. So, preparing those utility poles to receive a new fiber attachment. And so the technology, the Voxelmaps collection and processing technology can be used to do the clearance analysis or space allocations, and then that can be then fed into your pole loading analysis, right? Or creation, if you're looking at doing make-ready diagrams. And so it really feeds into that. It's part of that whole make-ready workflow, right? So we're not doing everything ourselves. It's feeding into the systems that you already have today, giving it quality data as you move forward. We've also seen lots of interest, especially with all this replacement of traditional lighting with LED lighting. So the Voxel technology and our collection capabilities allows for a really rapid inventory of all the lighting assets, whether it's a local government or a utility or really any entity, and then do automatic classification by lighting type. So with that, the training of the algorithms to be able to go in and extract that information. So you can see in these images, that bottom image is actually the identified or classified poles, and then the system will then auto vectorize those and put it into a format that you could consume within your GIS, like a shapefile of that. So it's a pretty complicated process that gets simplified through the voxel structure. An area of great concern, especially with the wildfires we've been having, is just this, vegetation management of encroachment. So in this case, utility infrastructure asset capture using the mobile lidar, so driving the streets, identifying all the assets, and then using our AI and ML based automated feature extraction, extracting and identifying vegetation versus non-veg features, poles, conductor lines, and then we can take that and then create buffers, around any of those assets. So you can take a conductor line and say anything within 3 feet I want to identify, right? And then do a quantification of that vegetation. And I've got a couple slides to show you what I mean by that. So in this case, we have an area here. This is an image. These are the RGB values assigned to the voxels. Now, interesting couple comments that I've got in the past webinars we've done is, why does your imagery look so pixelated? Well, this isn't the image, right? What we're creating is a map for a machine, right? And that's what Peter had talked about earlier. So this has lots of intelligence associated with it that the machine and our AI ML capability will then use in its process. So it's to the machine, this is a really pretty picture, right? And so again, what we've done is we've taken the voxels and colorized the voxels with the RGB value based on that 12 megapixel camera image that we collect. And then from that, we can create these, taking all the conductor lines. In this case, what we did was we took all the conductor lines and then did a buffer analysis at various distances and then color coded those to identify. And so then here I have the entire data set. This is just a different view looking down the line. And so we took out the veg that has the highest encroachment. And then you can see here, as we go through, we're just pulling out at different levels, different distances, how much the actual the vegetation, okay? So you can identify that, get it down to where there's, nothing within, say, 3 meters of it or 4 meters, which is good. But, from the overall view, this is this area that we collected, and you can see, at least in this area, there seems to be lots of veg encroachment, right? So it's something that you need to identify, but even more important is to quantify. So in this case, we took the areas of the closest encroachment, and then this is in the lower right there, that's a report out of the system, which is basically a CSV file that shows us the lat longs of the and the height, the altitude above ground of the minimum bounding rectangle, minimum bounding box, and the number of voxels within that, and then the volume of vegetation within that. So you can use that to feed into your work order management system for all the, to roll a truck out to do vegetation removal. And then you have basically an understanding of how much vegetation they need to remove, okay? So pretty solid capability. On the telecommunications side, we've done a number of projects such as this, where it was the end customer was looking for change detection. They were looking at, where have the new 5G antenna assets been attached to poles, right? So we had a baseline data set, and then we redrove this particular city, which happened to be San Francisco, and we had trained the algorithms of our system to identify those antennas, and then had identified the antenna locations, the poles, and gave them a location of that particular asset and height above ground, et cetera. And so really that's all they were interested in. Is I'm not interested in the poles without assets, right? I'm only interested in the poles where I had placed my assets. Did that asset get set at the right height? Did it get set at on the right pole? So really a validation of the contractor's work orders. We've also done some work in the area of 5G signal mapping. So in this case, we built a digital twin of a particular geography. This happened to be one of the larger US cities. And so we drove the entire city and then created this digital twin model of the area. And then we took the known locations of their 5G antennas and determined and did signal attenuation and propagation models from that, and then created these coverage maps. So if you look at it in the middle image there, you can see those floating voxels. Those are basically 5G signals, right? And so you can determine where you have dead zones from your 5G signal. And in this case, we actually did both external as well as internal to the customer's facility. So we did an internal collection of their buildings, used the propagation models of 5G through the building, and provided them with reports on where they had dead zones within the facility as well as external to them. This is probably one of the most exciting projects or pilots that we've done recently. So this is really for support of some HD map creation and autonomous vehicles, or AVs. So historically, what we've done is, and I should say not we, but everyone, is that there's data collection and harvesting via these mobile mapping sensors, right? And then what tends to happen is once the data is collected, those hard drives are shipped to a data processing center. All that data is then processed. We do data corrections, PPK corrections is required, merging of the data. And then we do the voxel-based AI feature extraction and create this high definition map, right? And then deliver that to our customer, who then gets it out onto the road into the existing autonomous vehicles on the road. That process is anywhere from 4 to 6 weeks at least, right? So a short time period in the grand scheme of things, but in the world of autonomous vehicles, they want something much more rapid. So what we did was we worked with Verizon as well as Amazon Web Services, AWS, and we had a concept, and we worked together to validate whether or not this was feasible. So in this case, the Symbo system was outfitted with a 5G Wi-Fi. The data was then, as we collected the data, we passed the LiDAR data to Verizon's 5G Edge network, their high-end 5G network. And then that data was then consumed within the processing engine of AWS Wavelength. So Wavelength is an AWS instance that actually sits at the telecommunications facility. So instead of going across the network, I should say, to the Verizon facility and then across the internet to AWS, it's actually right at Verizon. Okay, so we took that passed the data, the data across the 5G edge into wavelength, processed, created the voxel model, and then created a 3D model, and then did the automated feature extraction, and then took that data and sent it back across the 5G edge to the autonomous vehicle on the road. So basically took what has been a 4 to 6 week model and delivered it in about a 15-second average time frame. And again, we're not passing the real heavy image data. This is really focused on this case study on the 3D data, the LiDAR data. But it really, it showed that, using these 5G bandwidth and MEC, mobile edge computing for this super low latency computing can be achieved. So we've also done a number of voxel-based indoor visual positioning systems for using automated miniature robots. So in this case, what I was thinking to show this today is that a number of you from the utility side, maybe in the generation business, the electric generation business. And so you may have facilities like nuclear facilities or any sort of indoor facility, and you'd like to get a visual or create a three-dimensional model of that. So I'll start this, and Peter's going to give you a brief description of what's happening.
Yeah, thanks, Brian. So this is really interesting, actually. There's 3 views that everybody can see here. Okay, so in the bottom view is the voxel map, the indoor voxel map that we've already created of the building. So this was pre-created by us. The top 2 views are the camera information from the AMR, from the automated miniature robot. So the one that we can see on the left here, this is the RGB camera from the robot. So as it's moving around the environment, you can essentially see the progress. And then the one on the right is actually showing you what the camera's doing. And so it's actually recognizing different voxels from the voxel map, triangulating its position so it can localize itself without GPS or anything else, to a few centimeters in terms of accuracy, and then updating its position relative to the voxel map below. So if we just play the video, so it just calibrates itself when it's first started. You can see in the top right now, this is the detection. All of these lines that you can see are essentially the recognition events. So these are the lasers going out and recognizing these different groups of voxels and triangulating its position. The camera on the left, you can see as the AMR is being moved around the environment, it's recognizing where it is and it's updating its position accordingly from the voxel map below. So this is a scenario that we're now starting to use. This was done for a major US corporation. This technology is now starting to be used inside warehousing. And so for the AMRs moving around warehouses, not just to create the map and position themselves, but also to do real-time indoor updates of the map data as well. And it has the ability not just to do it obviously on the X and Y, but also looking at high resolution on the Z axis as well. So this example of it going upstairs is illustrative of that.
All right. Well, thanks, Peter. I wanted to share with you a couple of other use cases and projects that we've done just to show some additional capabilities in other industries where we've seen success. So in this case, we did a project where we did basically a traffic sign data collection inventory for a major navigation company. So we drove many miles of roads to identify and then automatically capture the sign information and then do annotation of what that particular sign is. We collected over 7 million signs, so a pretty large project in terms of that. And then we converted that into a XML format for the customer to consume. Installation compliance. So in this case, it was for local government. So they had contracted to have assets updated or added to their into their right-of-way. We went ahead and we did a driving collection using the Symbo system, and then looked at change detection on existing assets. So we had their existing assets in a database, a spatial database, and then used the new data to do automated feature extraction. We did automated measurements as well to make sure that, like new signs put up in the right of way met all the compliance issues that are required for those sorts of signs. We've also done a lot of road network mapping for a major automotive company. In this case, creating HD maps for autonomous vehicles and, creating full lane models, traffic signs, identification, all the striping. And, just to give you an idea about the size of some of the projects that we've supported, last year in North America for a customer, we drove a little over 650,000 miles of roadway. So pretty significant effort by our teams across North America. There's also a lot of talk about smart cities. So in this case, using digital twins to support the whole urban planning, and it can be used for a wide variety of use cases within the city. So it could be, any sort of infrastructure monitoring or assessment, city mapping and updating of city base maps, or looking at detecting environmental changes. So maybe removal of vegetation, or planting of vegetation, or things like historical preservation, right? Where we have an existing model of a building, and we can then work to keep it at its current historical level. The automated HD map creation. So we've talked a bit about that, just being able to collect networks and build these models for consumption by the autonomous vehicles. And then, in the whole autonomous vehicle space, one of the things I wanted to briefly talk about is this concept of constant collection network. So one of our plans is to have fleets of vehicles with lidar and camera. So not like the whole Symbo system, but much smaller units with like a single lidar, single camera, but constantly collecting data and feeding it into the Voxel archive, and being able to, at the time of collection, transmit that data back to a central Voxel database, and share road conditions and everything else. And that's part of this whole vehicle to everything market that's going on right now, and you'll see that expanding in the future. Other sorts of things like smart parking. So you could use this vehicle to everything to identify, when somebody pulls out of a spot, then it gets identified as open and can direct people to those particular spots and potentially save on fuel consumption. So that gives you a quick overview of some of the broad use case capabilities of Voxel Maps and our technology. What I wanted to talk about as well is this U.S. Senate Infrastructure Bill, HR 3684. And so there's lots of talk out there about it, but I thought I'd share some with you. And it's not, when it talks about infrastructure, it includes power infrastructure. There is monies in there available for organizations on the power side as well. So basically, this bill authorizes funds for federal aid for highway safety program, transit, utility programs. In reviewing this whole text, you're more than welcome to read through the 2,700 pages if you desire. If you can't sleep at night, I would suggest that. But there's a significant emphasis on geospatial modernization and innovation. So, for those of us in the geospatial industry, I mean, if you're on this call, I would say you're involved in that space, but it's a really good thing for us. And this just shows that, over the next 8 years, there's $1.2 trillion. But a couple of things that, would tie into the utility space. One is, electric vehicle infrastructure, right? That's $7.5 billion. Electric buses, right, for transit, 7.5. Infrastructure, or excuse me, broadband infrastructure. Look at that, $65 billion, right? And then 73 billion for the power infrastructure. So I think what this shows is that for those in the utility and telco business, there's some nuggets in there, right? And if you're involved in that space, you should be looking at this. And I have one more here, but from the side of technology, so you're not going to find digital twin or digital cities or virtual reality or augmented reality in the bill, right? They're probably, they determine probably two specific dimensions, but to fulfill those goals for digital twin and digital cities, the bill outlines the funding to fund those without naming them, right? And so one of the key areas as well is digital construction, and that's an area of heavy investment as well. And then on the 3D side, what we see is that this bill will be the catalyst for many groups and entities, customers, to finally take that full 3D or the Voxelmaps 4D plunge and start just building out these digital twins of all of their infrastructure and their service area as well. So we've actually put together a pretty solid white paper that talks about this. And so if you're a part of this event, you're going to get a copy of that. And we'd ask that you share that, and we'll be promoting it out there. It's really it's an educational piece, so it's not a marketing piece. It's produced by Voxel Maps, but it's about how do you understand what's happening in this infrastructure bill and what it means to you, and the funding available across the number of different markets. So Peter started off today and gave us an overview of Voxel Maps history and rich history of digital mapping. He then talked about this whole concept of maps for machines, and I hope you understand what we're talking about there, because it is a really different approach to mapping, and it's one of the unique capabilities that we bring. The whole volumetric mapping 101 technology and what that means for you in terms of mapping and the use of LiDAR and imagery. Briefly talked about the data collection capabilities of our Symbo system and the new Symbo system, which we're really excited about getting that on the street. He then mentioned the 100 Cities project, and we're going to be getting that whole fleet of Symbos out there collecting data over the top metro areas in the U.S. and building this, this 4D volumetric archive. I then talked a little bit about some of the utility industry use cases and where it can be used in utilities, as well as some telecommunications and some other areas, and closed it out with just a couple of slides on that infrastructure bill that we thought you would find interesting. So with that, we're going to open it up to questions. And I see here we have a lot of questions, which is very good thing. So I will read the question, Peter, if you can answer some of these. So the gentleman, I'd like to generate 4D hyperspectral voxel maps from multiple camera sources taken at the same time. Is this possible?
Yes, provided that you've got a point cloud. So we do a very similar thing actually when we do aerial collects. So some of the data we collect is not just from the mobile mapping sensors, we also have aerial sensors as well. So in those configurations, we're using actually 5 cameras, 4 obliques, one that's looking straight down, and then the LiDAR. So it's important we have the point cloud to generate the voxels. Once the voxels are generated, then we use the 4 angles of the camera to be able to colorize then the voxels, so it can be done. If you're talking about camera only, so you're not having LiDAR, you have to do something like structure through motion. It's possible to generate it, but the quality will be lower in comparison to if you use the LiDAR as part of that collect.
All right. Thank you. So another question, what size is a voxel?
So a voxel can be any size. I mean, the whole point of this model is it's multi-resolution. It's not just one fixed resolution. So typically we're using 1 to 4 centimeter voxels, but they can be smaller than that if the hardware can support it, or they can be obviously much bigger for things that you don't need a lot of resolution for. Right.
And as you talked about earlier too, Peter, that in areas where the LiDAR signal passes through and doesn't hit any object, those voxels are 8 meters in size.
Yeah, exactly.
Yeah. All right. Somebody asked, what is the drag coefficient of Symbo?
Good question. Not entirely sure necessarily why you need that. I mean, the drag coefficient is quite small, so it's not actually putting a lot of force, on the vehicle that it's fitted on. So it's 4.6 from memory, somewhere between 4.6 and 4.8.
Thank you.
Sorry, 0.46, 0.4. Yeah.
All right. Somebody asked if a given utility project, they're using this for putting 10,000 miles of utility transmission lines underground, and not at the current time, Daniel. What's the most efficient way for the BIP software to receive and access collected data?
Yeah, so the typical pipeline that we have is that we actually provide a processing private cloud. So this is quite big infrastructure that we have, where we take then the streams of the data, which can either be offloaded in real time if there's 5G, or physical hard drives, or some other form of transfer. And through that private cloud, we process the data and do the extraction and hand the data back. It is possible to do custom installations of projects. Generally speaking, that's quite expensive to do unless you're talking about a huge amount of data, because the servers required to do the processing are very powerful. They have many, many graphics cards inside them as well. So generally speaking, it's cheaper to use our private cloud to do that.
Right, and that was one of the other questions. Do you host data on our servers for the web interface? And then could they run our software on their own servers?
Yeah, most use cases we're running on our own infrastructure and providing access to people. But for the right use case, yes, we can deploy within an organization as well. There's some talk around that in terms of some security applications or government applications, for example. And yes, that's possible.
All right. Here's another good question. For vegetation management, to get a complete model, do you need to integrate aerial, drone, LiDAR, and imaging?
I would say it's good to have it. It very much depends where you're trying to collect. So, for assets that you can't see from the roadway, then yes, definitely, aerial makes a lot of sense. And if you're looking at transmission corridors that are completely away from a city, then aerial is still the best way of collecting that data. But for us, again, we're agnostic from how the data is collected, as long as there's good quality LiDAR involved in it as well. So if it's been collected from an aerial LiDAR source, we can take that and automatically ingest it as well.
Okay. What is your starting point for creating a voxel map? For cities where there's no prior data, you have to start data collection and analysis from scratch.
Yeah, pretty much. And that's what we do. That's kind of been the history of the company even before, the company started, when it was part of the large company in terms of NAVME. So we're very used to doing that. So we go out, we work in one of two ways. One way is where a customer will come and tell us what they need to have mapped. And that can be a city, it can be a state, it can be an entire country. And we've done this at country scale many, many times as well. For our own 100 city data, we have a schedule, and we can definitely share that with everybody. If you're interested, then do let myself or Brian know. We'll explain where the 100 cities are and the dates that data will become available.
All right. Have we done any BIM objects, walls, doors, stairs, etc., AI feature extraction into the IFC data schema, or could it be done?
Yes, absolutely. So the answer is yes on both accounts. So we've worked on BIM models, exporting into various CAD applications using the IFC schema as well. So yeah.
Okay. Has any work been done in agricultural settings and applications, especially for ag robots?
Not specifically for ag robots. That would be an interesting one for us to do. But in terms of agricultural settings and kind of rural environments, yes, we've done quite extensive collects in forest areas and countryside areas, in jungle even as well. So a slightly different use case, but using the same technology and same approach.
Right. Here's a good question. Can the AI feature extraction pick up features that are flush with the surface, such as manholes in a street surface?
Yes, yeah, absolutely. So it can do. It can see that both from the voxel side. There are times where sometimes 2D extraction is very useful as well. So for example, sign information. Some signs you can read fully in 3D, but sometimes it helps to have a 2D image. Now, all of the images that are collected as we drive the Symbos around also match onto the voxel data. They're kind of like a metadata layer. So we can actually extract additional kind of detailed information or semantic information from those images.
Right. Another question, have you tried to use this for marine applications, nearshore mapping, or with bathymetric lidar?
Yeah, we just finished off doing a scan actually with Bathymetric Lidar, actually in San Francisco. So I have to admit, it's a relatively new area for us. So it's not as if we've done a lot of projects there, but we have a few partner companies that are extensively collecting data in the oceans, and we're actually modeling that for them as well. So absolutely, it can be used to do that.
Okay. Cool. This is a good question here. Since the digital twins are a bridge between CAD and GIS, but typically data for CAD falls into the engineering and surveying realm, and that requires involvement of a PE or a PLS. We have thoughts about what may resolve future issues as these technologies evolve.
Good, yeah, no, good question. So I think it's interesting, really, in terms of there's different kind of use cases within departments of how to obviously use this data, and where it falls into. One of the things with creating a digital twin in this way is it creates a data abstraction layer, and so from this abstraction layer, you have the ability to export into different formats to support the different needs of the organization. One of the things that we're kind of very active on at the moment is integration into kind of the key software applications that current customers are using. So all of the big names, for example. And so we're facilitating more and more of that. So it makes sense to collect, store, process the data as a Voxelmaps digital twin, but then you have the full flexibility of being able to push it into different data formats and connect it to different applications for different groups.
Okay. Just looking here to see if there's any other questions. That's really about it. There was another one on if I collect transmission line, somebody's involved in the transmission side of the business. Many of their sites, their assets are available via mobile, so they get collected via vehicle, but some of the others are only available via aerial. Can they use Voxel maps for that? Yeah,
absolutely. So we don't currently at this point in time, we don't do aerial collect ourselves. We work with partner companies for doing aerial collect. So the aerial data is collected either using obviously helicopter or plane, or in some situations UAV, and then we can take that data and then model it and do all of the same things. We also do a similar approach for data that's not collected from vehicle or aerial, where it can be walked, so pedestrian types of collection. So there are backpack versions of the hardware which will be able to generate the data, which we can then convert into a voxel map and do all of the processing as well. That's also used extensively in the indoor mapping space.
All right. And then I will just say that, on the distribution side, there's sometimes when aerial collections, you want to get a view of an asset like a cross arm, right? And so in that case, you could integrate both either a aerial or a UAS collected imagery with the Voxelmaps symbol collected mobile application as well.
Yeah, absolutely. And I think, the key thing to point out is a lot of the screenshots we've shown here, these obviously literally just 2D screenshots from the application, but the applications themselves are fully 3D. So you have the ability to look around in 3D as well as all of those things. So it's not just taking one view of the asset, it's looking holistically at it.
All right. Okay, I think that's it. We want to thank everyone for participating. Again, we'll be sending out a guidebook with links to the webinar, the webinar recording, and you should feel free to share that with anybody within your organization. And that will also include the infrastructure bill white paper will be incorporated into that guidebook as well. I think you'll find that some very interesting reading, because we just we tried to take the 2,700 pages and put it down to about 6 or 7 pages to help you understand what's in there, what the opportunity is for the geospatial community. With that, we'd like to close it out. And again, thank you for your participation, Peter, and I truly appreciate it. Cheers.
Thank you very much, everyone. Goodbye.